elegant way of thinking about energy and work. It's going to require you to unlearn a couple of things. One of the things that you're going to have to unlearn is something I actually taught you, but I warned you. So hopefully it won't be too tricky for you to unlearn this. And then one of the things you're going to have to unlearn is something that has been a hallmark of physical science classes since you first started learning about kinetic energy. The very first time you heard about kinetic energy, there was this big differentiation made between kinetic and potential energy. Those are sort of flip sides of the, one is one thing and one is another. And in order to really understand energy transfers and conservation of energy, we have to lump them all together. And kinetic energy is really not any different than other forms of energy, including the two forms of energy that we've looked at so far, elastic potential energy and gravitational potential energy. It is true that kinetic energy is unique and that we can see something moving because of it, which is great, but it's actually, aside from the fact that we can see it, it's really no different from other forms of energy. So the big thing that we're going to be working on, we'll start this today, continue next week. We only have 2 days next week, Monday and Tuesday, both all days, but we'll continue working about this. It's what I call telling the energy story. And what the energy story involves is being able to look at a scenario or hear a description of something or observe the actual events and explain where the energy is, how it's getting moved around. And that is going to involve talking about potential energy, kinetic energy, and work. So the energy story, it ties all those things together. Now, a lot of times in a real world situation, we're not going to be able to quantify all of these things at every moment. In a simulation, we can, and in certain engineered situations, we can as well. But there are going to be plenty of times where it's just too complicated to try to carefully quantify these things, but we can still qualitatively describe them. We can still say, well, I don't know exactly how much energy is here, but I know it's got to be more than there was a couple of seconds ago. I know that energy must have gone from here to here because of this work. So we'll be able to qualitatively describe stuff. And that's what I call the energy story. And then in a more quantitative sense, we're going to take all this stuff, put it together, and use it to be able to make predictions. And the predictions that we've made so far have to do with how fast is something going, which is often the question we care about, like how fast is this going to be going? If we set it up on a hill and launch it from a spring, how fast is it going to be going at the bottom? That's a reasonably important question. But when we put all of this stuff together, you'll realize there's lots of other predictions that we can make, and it gets really complicated and really kind of fun to think about. So I want to start with conservation of energy. And this is something that the level that we're going to be using it is not a difficult concept. Basically what it boils down to is, remember our definition of energy, which isn't a good one. We don't really know what energy is. It's not a definition that gives us any concrete way to think about energy. It just gives us an explanation of what energy does, but that's pretty good. And so our working definition of energy is some property of stuff, materials, waves, fields, whatever, that allow them to speed things up. Energy is the ability to speed things up. If we look at the entire universe and add up all the energy that's out there, it turns out that no matter what we, where it is, how it changes, it's always exactly the same. The total amount of energy in the universe is constant. And while that's not particularly helpful for us, since we don't know how much exactly energy is in the universe to begin with. I mean, we have some pretty good ideas, but what ends up happening is, because we figured that out about the universe, we were able to sort of scale that down to smaller things, and what we recognized is, oh hey, if we just kind of keep track of where the energy is and where it's going, we can make some assumptions about, like, well, most of it is still going to be there at some later time. Yeah.
If, like, you charge your phone and your phone uses like electrical energy and it dies, what happens to the energy?
Yeah, that's a great question. So, so as energy gets moved around, it's never lost, it's never destroyed, but it can exist in forms that are less useful to us. So what happens to that energy in your phone is ultimately it all becomes heat. That's it. Your phone heats up. Even the screen itself, the phone screens use a lot of energy. If you look at your phone a lot, it by far that uses the most energy on your phone. Well, those photons that are leaving your screen eventually end up just heating stuff up. And nothing ever gets hot from the light from a phone screen because that energy is radiated out in such a diffuse way that it doesn't create it's not like a little hot spot that you would get like with a laser or something, but it's effectively the same thing, yeah. So it's not gone, it just heats stuff up. And then that heat isn't as useful to us. Electrical energy is really useful to us because we can harness it with wires and we can make it do stuff. Heat, less useful. We can use it, and we do. And in fact, in your lifetime, one of the things that's gonna be really interesting to see is how we take heat energy that currently we just think of as waste and use it to do stuff. Like, we can use heat to generate electricity. If you take heat and you use it to boil water, and the expanding water vapor pushes on something, and we can use that to make it like an electrical generator. That is how a nuclear power plant works, right? Like that, we're not like setting off bombs in buildings and then just plugging something into the bombs. Nuclear power is basically boiling water. The energy to boil water comes from nuclear reactions. They heat up water, that creates steam, that pushes on a turbine, that makes a differential electrical charge. That's what ultimately allows nuclear power to make stuff go. So in your lifetimes, it's very likely, because we're moving toward a system where much of our energy is electrical rather than fossil fuels, it's very likely that we're going to start harnessing that excess heat energy. So something like this, where I'm heating up my water on a little burner, there's heat just escaping from this. Most things in another 10, 50, 20, 100 years are going to have heat exchangers that'll trap that heat and use it for something else. I should say, I don't know that for sure, but it makes sense, right? Why waste that when we could use it to generate electricity? That kind of thing is called cogeneration, where you're doing two things at once. Anyway, so the point is, if we look at the whole universe, all the energy in the universe is always the same. And we don't care so much about the universe in the context of this class, but we can take that same idea and scale it down to relatively short-acting situations. And in particular, we're going to be looking at mechanical energy. And when we look at mechanical energy, we're looking at energy that we can relatively easily harness to make something go, that is stored in the shape or structure or location of something. What is energy? Energy is the ability to do work. What is work? Work is a transfer of energy. What this means is, well, first of all, that's sort of a circular definition, right? We define energy in terms of work, and we define work in terms of energy. Those are mushy concepts. But what basically this means is that if we have some energy here at one point, and it's gone at some later point, then it went somewhere. It was transferred somewhere else, because energy can never be destroyed. If it's transferred something else, it must have been work that did that transfer. And that's where we're going to put together our energy story. It's the idea of how work moves energy from one storage location to another. So going back to the cell phone question, there's work, right? Like there's electrical energy in the wall, and then all of a sudden that energy is in a battery. How did it get from the wall to the battery? Work. There must have been work done. Yeah?
So wait, does that mean that energy can be transferred like infinitely?
Yes, and in fact, it is transferred infinitely. But it's a weird one-way street. And we're not gonna talk about that in here, but if you look at, there's all sorts of cool stuff out there on entropy, and you learned a little bit about entropy in chemistry, right? Entropy is disorder. So it's a one-way street in that all energy is eventually gonna end up in the form of heat. And then we're gonna have sort of this, like, so things will be relatively static, it won't. But the amount of energy is fixed. Right now, we have a lot of highly ordered energy. And so we can kind of pass it along, and we can even, what we do is we sort of borrow, right? So we can bump things up on the energy scale. What we're really doing is taking some really organized energy and making it far less organized. We're taking some less organized energy and making it a little bit more organized, and that ends up paying off for us. That's charging your phone. We're taking electrical energy, using it to create order in your battery. In doing so, we generate a lot of heat. Charging a battery increases entropy. It's really, really fun and crazy stuff to think about. Yeah?
Did you just explain global warming?
Did I? Well, yeah, I mean, actually, yeah, I mean, it's not exactly the same because the amount of heat so when the sun's light hits the surface of the earth, it is transformed, much of it, into infrared radiation, which is one form of heat. And global climate change has to do with the fact that as we change the nature of our atmosphere, less of that heat is radiated out into space and more of it stays on the planet. So yeah, it is. It's an energy transformation. There is work that's being done. It's all the same stuff. Really, really neat to think about. Okay, so let's build our analogy. So the first thing is we are going to dispense with the idea that there is something like fundamentally different about kinetic energy and potential energy. It's all just energy. It is different, but it's no more different. Kinetic energy is no more different from, say, elastic potential energy than elastic potential energy is from gravitational potential energy, or that any of those things are different from chemical potential energy. It's all the same basic thing, which is the ability to speed something up. Kinetic energy is the ability to speed something up because something is already moving. Something's moving and it hits something else, it can speed it up. Therefore, its motion had kinetic energy because that energy could be used to speed something else up. What happens? Work must have been done. You have to have work for energy to be transferred. Chemical potential energy, the same thing. If I light a campfire while I'm camping, and I burn the wood, there is energy, I can feel it, the light, the heat from the flames. Well, that chemical potential energy has the ability to do work, and we often make chemical potential energy directly into a force applied over a distance. That's how vehicles work. Even a car is running on chemical potential, even an electric car is running on chemical potential energy. It's just that the chemical is different from fossil fuels. But same idea, it's chemicals in a battery that react, and that reaction transfers energy from the chemicals themselves into kinetic energy of your vehicle. So the way I like to think about it is that energy is like money. Okay, so money is the currency used to buy goods. If I have $5, that's how much stuff I can buy. And energy is the currency that we use to make things go more quickly. That's what energy is all about. It's about making things go faster. The more energy you have, faster you can make something go. Doesn't matter if that energy is in the form of kinetic energy, gravitational potential energy, or elastic potential energy, or some combination. It doesn't. The more you have, the faster you can make something go. With money, If you buy something, it's called a purchase. What actually is happening in a purchase? Well, the money that you have is transferred from you to somebody else. In energy, in the world of energy and work, using energy to make things move is called work. So what does work do? It transfers energy from one thing to another thing. So energy is like money, work is like purchasing. Energy is the noun, work is the verb. Okay? And just like energy, if we quantify the amount of money in a certain environment, like in this room right now, if we were to add up all the money that everybody in here has, maybe like all the cash that you're carrying on you right now, maybe it's like $25, and you add that to the cash that I have right now, I have like $6,000 or $8,000 in my pocket. If we were to add that together, the total amount of cash in this room is like $7,025. I mean, none of you are surprised, right? You know, I mean, that's small change for me, right? I mean, look at my bling. You think this is cheap, Ethan? I walk around with thousands of dollars in my wallet. It's just what I do. So if we were to quantify the amount of money in this room, it would be a certain amount, but we just had somebody walk in. She might have some money. And if sorry, that really was an awkward way for you to enter the room, but just, we're not gonna rob you. So you too, you might have some money. So if money comes into the room from outside, then we've increased the amount of money in the room. But we can kind of control for that. We can sort of see it happen. The same thing happens with energy. If we have a system and we have some control about whether energy comes in or whether energy goes out, then we can kind of like batten down the hatches, especially for short periods of time, and say, okay, well, the amount of energy in this scenario is always going to be the same. So if you have a ball rolling along a level surface, it has some kinetic energy and it has some gravitational potential energy relative to lower points. So it might be rolling more slowly, when it goes down a hill, rolls more quickly, rolls back up the hill, rolls more slowly. If we sort of say, well, in this situation, I can imagine that not much energy is being added to or taken out of that whole system, we can reason that the sum of the gravitational potential energy and the kinetic energy at all times is going to be the same. If we add these things together, we're always going to get the same amount. The potential energy is going to change. Has less potential energy at the lowest point, has more potential energy at the highest point, gravitational potential energy. The kinetic energy is going to change as well. Has less kinetic energy here, and has more kinetic energy here, and it has, like, kind of goes back, this looks like it's about the same height, so I would say probably it goes back to having about the same amount of kinetic energy as it did originally. But as long as there isn't anything that is speeding this up, right? As long as there's no energy being transferred into this system, then we can say that the sum of those two things is always going to be the same. And that is how we're going to build our system that we use to evaluate conservation of mechanical energy. So mechanical energy is just a subset of energy, and it's easiest to describe it. So it involves pushes or pulls, but there's not complex reactions, there's not heat, there's not electromagnetic waves, there's not a whole bunch of stuff. Basically, the easiest way to think about mechanical energy is that it involves three things. One, gravitational potential energy, that's a form of mechanical energy storage. Two, elastic potential energy, that's a form of mechanical energy storage. And three, kinetic energy. Those three things together are what we typically think of as mechanical energy. So energy that's stored in deformation or gravitational fields or motion. Those three kinds of energy are what we think about as our mechanical energy. So gravitational potential energy, elastic potential energy, which we're going to use springs for, but it could be any kind of deformation that that it, like, where there's some sort of restoring force, and kinetic energy. Those are the three places energy can be stored. And we're gonna engineer situations in which energy is not really added to any of those areas from outside, nor will a ton of energy be removed from all of those three sources combined. Some of it will be. It always happens that we have some energy loss. We're not gonna think about that today, but we will think about that next week. But if we think about these three places as being the only place energy is really stored in the systems that we engineer, then we have an equation that we can use, and we'll come up with it in just a second, but basically that's gonna relate the amount of energy that's stored as kinetic energy, gravitational potential energy, and elastic potential energy. And here's how we can think about it, right? So what we're gonna imagine is that in any given system, at any one time, there's a certain amount of kinetic energy. It might be zero, but it could be more than that. So we can think about this as like something in a bucket, right? So we have this much kinetic energy. There is elastic potential energy that's stored in deformation of things. That can be like a spring, or it could be other things as well. There's all sorts of things that can store elastic potential energy. We're mostly gonna think about it in terms of springs, but keep in mind that any one system could have more than one spring. So for example, if we have two carts moving toward each other, there's two springs potentially there. Each of those carts has a plunger. If they move toward each other and both those plungers squish, then there is energy stored in each one of those plungers. So you can have more than one spring. It's not like there's one spring. It's a whole accounting system that looks at all the elastic potential energy. That could be zero, or it could be some amount that's non-zero. And then there's gravitational potential energy. And what we talked about yesterday, Tuesday, was the idea that gravitational potential energy doesn't really ever get to zero. There's always some gravitational potential energy because everything in the universe is being pulled on by everything else. So you can never say there's no gravitational potential energy. But what we do is we take the lowest amount of gravitational potential energy in any one situation and just say, okay, well that's zero. It's not really, but let's just call it zero. And then anything that is above that point has gravitational potential energy relative to that point. With gravitational potential energy, if you want to keep things as simple as possible, always identify the lowest point that anything will be in whatever system you're looking at. So when we go back to your falling objects, things that are moving down ramps, curved or otherwise, just find the lowest spot and say, I'm gonna call that zero. That's height zero. Everything above that has gravitational potential energy. Is there gravitational potential energy at that point in an absolute sense? Yes. If you happen to mess up, if you take your ramp and you put it on a table, and your idea is to see how fast something is going when it gets to the bottom of the ramp, if it goes off the ramp and falls off the table, then it's going to accelerate as it goes. Things have gravitational potential energy at a tabletop relative to all the points below them. So it's not zero, but we can say that if this is the lowest point that anything's going to occupy in our system, then that is, relatively speaking, zero. That's the lowest. We're going to call that zero. Everything else will be positive. Okay. So let's say, let's like engineer a situation like this. Let's say that we have a supercar, and it's at almost the top of the ramp, but not completely. Okay, so it has some gravitational potential energy. It's also moving. So let's say we're looking at it not right at the beginning when I'm holding it still, and not after I've completely let go. But let's say that we were to make a movie of this supercar being launched. And what you would see is, as soon as we press the button, it starts to speed up. The spring unwinds, and it's going down at the same time. There is a very short amount of time when it's moving. It's not at the very top of the ramp, but it still has a long way to go before the bottom. And the spring is still partially squished. That means at that moment, we have some amount of kinetic energy. The cart is moving. There's some amount of gravitational potential energy. The cart isn't at its lowest point in the system. And there's some amount of elastic potential energy. So we have some energy in all three of our buckets. Energy gets moved from one bucket to another bucket through work. What's work? Work is force applied to something over some distance in the direction of that force. What's going to happen here as that cart moves from the top, close to the top of the ramp, down through the middle of the ramp, and down to the bottom, is that all of this elastic potential energy and all of the gravitational potential energy are going to be transferred into kinetic energy. How does that happen? Well, the elastic potential energy gets transferred as the spring pushes on the car. That's work, force times distance. All of that elastic potential energy is gone as soon as that spring is fully expanded. So within like a tenth of a second of letting go of this cart, all of the elastic potential energy is gone. Okay? And it was transferred into the kinetic energy of the cart. What about gravitational potential energy? That gets transferred into the cart as well in the form of kinetic energy. How does that happen? This is the gravitational field pulling. This is the gravity spring. So just picture a spring connecting this cart to the very center of the earth. As that cart moves down the ramp, the spring gets a little bit more compressed. Not very much, but just a little bit. That causes the cart to speed up. That means that at some later time, when the cart is all the way at the bottom of the track, hasn't hit anything yet, but it's almost about to hit something, there's basically no gravitational and no elastic potential energy. All of the energy is now stored as kinetic energy. Now you all know what would happen if, for example, we took a cart down here and we set it up with a spring and we did exactly what I was just describing. So we have a super cart in, right? We have a super cart up here. I'm going to launch it and it's going to go down the ramp at the same time. Oops, that was terrible. Let me try it again. I need like 11 hands for this, unfortunately. I think probably I just want to push the button down. All right, let's try again. This time I'm going to not try to push the button. So off we go. And you can see like, well, so what happened? Because if energy is conserved in this system, it seems like we should have seen something different from what we just saw, where it just sort of stops at the bottom because now there's no energy. And the answer is that any time there is a mechanical system, some amount of energy is transferred into what we call thermal energy. And we'll look at this more next week. But no matter what we do, there's going to be some energy that we can no longer account for. We'll talk about thermal energy later. Okay? And if we wanted to, we could also think about any work that was done by the system that we're thinking about to other systems. So for example, some of you noticed that when I rolled this cart down, it locked this spring. This spring wasn't part of our system originally. We weren't looking at it, but there's energy in here now. Our cart, as it got to the bottom, did work to that spring. So if our system does work to some other system, then energy is moved out of our system and into the other system. We're not gonna worry about either of these two buckets right now. We're just gonna stick with our 3 buckets of stored energy. We're gonna engineer situations in which no significant amount of energy is lost, like to heat, and there's no significant amount of work done to our system or done by our system to anything outside of the system. So what that leaves us with is a relatively easy statement, which is all our stored energy at any one time added up should be equal to all our stored energy at some later time added up. That gets pretty ugly if we start thinking about our stored energy, because we have 3 types of energy storage: our initial gravitational plus our initial elastic potential energy plus our initial kinetic energy. Those are the 3 ways we have to store the ability to do work. We add all those up, they should be equal to final gravitational and elastic potential energy plus final kinetic energy. As confusing as this is going to look at first, it actually makes much more sense to think about this in terms of variables. So what are we looking at? We're looking at initial gravitational potential energy. U is potential energy, the G means gravitational potential energy, the I means initial. Initial gravitational potential energy plus initial elastic potential energy plus initial kinetic energy should equal our final gravitational plus our final elastic plus our final kinetic energy. This is the simplest way to look at and think about this stuff, but we have equations for gravitational potential energy, right? It's our mass times g times our height above some low point. We have a way to look at elastic potential energy. It's 1/2 kx squared. For every elastic source of energy storage in our system, if there's 12 springs, we're gonna have 12 of these. We're only gonna deal with 1 spring at a time though. And then kinetic energy is 1/2 mv squared. So where we arrive is this, and again, it looks ugly, but it's not really. This is just the weight of an object times its initial height. That's its gravitational potential energy relative to some point, which we're gonna always pick to be the lowest point in our system, plus however much energy is stored in springs in our systems, 1/2 kxi squared, plus our initial kinetic energy. There can be 12 objects moving in a system. We're gonna just deal with 1 or 2 at the most, right? So we're gonna keep it simple, but all of those objects can potentially have kinetic energy. That's gonna equal the final gravitational, final elastic, and final kinetic energy. That equation is the big one. A lot of times, you're gonna have a system where 1 or more of these things is 0. So for example, with your ramp system, we have to make sure of a couple of things. One is, we have to make sure that we're not losing too much energy to heat. So that means we gotta reduce friction. The other thing is, we gotta make sure that our system isn't doing work to something else. So, there is work going on to something else. There's work going on to make the wheels rotate. This has no motion, like translational motion, it has angular motion. There's energy stored in the rotation of these wheels that we're not accounting for. Luckily, it's virtually nothing. It's hardly any energy stored in these wheels. They designed the carts so that there's not much energy stored in those wheels. So that means at the beginning of your, how fast is something gonna go when it goes down a ramp, there's no elastic potential energy. If your object starts at rest, all we have is gravitational potential energy. At the end, if it's at its lowest point, doesn't have to be, but if it is, there's no gravitational potential energy. There were never any springs involved with what you're doing, which means that all of the gravitational potential energy has been transferred into kinetic energy. That's where the word kinetic energy theorem comes from. That's the extension, is if we take all of our potential energy and let it do work till there's no more potential energy left, then the work that those elastic and gravitational potential energy sources do will be equal to the final kinetic energy of the system. If we were to look at this right here, this is kind of interesting. So let's imagine that we start a rock here with no velocity at all and hold it up a certain amount above the spring. We drop that rock and it squishes the spring and then it bounces back up. If we have perfect conservation of energy, which we won't, but it'll be reasonably close, then the rock should end up at the same height that it started, right? Like a perfectly conserved system, the rock will just bounce up and down off that spring forever. We'll have perpetual motion. And if we look at our system when the spring is completely sprung, there's no elastic potential energy here or here, which means all of the gravitational potential energy at the beginning is going to be equal to the combined gravitational potential energy and kinetic energy as the object is above the spring. It's going to be going fast here with relatively low gravitational potential energy, slower, 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 slower until it gets up to here where we'll have no kinetic energy. The only energy left in the system is gravitational potential energy. Where it gets interesting is this point right here. But we could say this is position 0. And then we can say, well, there's no gravitational potential energy here. Fair enough. But what happens as this spring starts to rise? As that happens, what we're going to see is that before the spring is totally sprung, it still has some energy in it. The ball is moving now. It has kinetic energy in it. And the ball is a little bit above the ground. So now there is some gravitational potential energy. Where is that potential energy stored? In the gravitational field, which is hard for us to understand, or we can think about it as the gravity spring. Imagine that there's 2 springs here. This mechanical spring that we can see, and the gravity spring that goes all the way down to the center of the Earth. As this object is lifted, our physical mechanical spring is doing work to the ball, which is doing work to the gravity spring. Energy is being transferred from our real spring to the gravity spring as this ball is moving up. Once the ball gets to this point right here, it continues moving up, transferring energy into gravitational potential energy. What does that mean? That means this object, if we think about our gravity spring, is doing work to the gravity spring. The kinetic energy from an object moving upward in the Earth's gravitational field is doing work. It is applying a force to the gravity spring, and it's applying that force over some distance as the gravity spring stretches out. And that is work. If we throw something up that's attached to a spring, the thing that's moving up will do work to the spring as it stretches it out. That energy gets stored in a real spring as elastic potential energy, 1/2 kx squared. In the gravity spring, since it's constant force, we don't have to worry about the 1/2. And we know that the amount of force is always the same, it's always mg. So in a gravity spring, it does mgh work as it gets lifted up. But it's a pretty slick way of thinking about this. This is going to take most of you a while to work with. We've got the equation to work with, we've got the energy story, the concepts to work with. We're going to play around with all of that stuff. What I want to have you do right now, though, is wrap up your work with finding the velocity of an object on a ramp, finding the speed of a falling object is what it's called. So just remember, the falling part of it isn't free fall. It can't be in free fall. But we had some brilliant ideas in here. We had some people go outside and look at the swing outside, getting on the swing. You could roll something down the slide at the preschool. We've got the curved whiteboards that can serve as ramps. We've got all sorts of ways that we can set up a situation in which an object goes from one height to a lower height without any work being done to that object except the work done by gravity. That's the key. We've got to make sure that there's no other work involved. That object can't speed up or slow down because of anything else. It can only really be affected by gravity. And if you want to take a break, now's a great time to take a break. And I can help you with this work as you do it. Keep the framework of the conservation of mechanical energy equation in the back of your mind because that's going to be helpful down the road.